Okay, so here's a couple of trivia things for you guys. So as we're standing on a mountain, right? And we just climbed the summit or something, and all of a sudden we notice this major temperature change, right? What causes the temperature change? I was hoping I could, draw on the whiteboard. I'm sure Steve knows that.
Just higher altitude, colder air temperatures.
Okay, what makes the air colder?
Less density of air molecules.
Okay, less density, less kinetic energy. So you know that, right? Yeah, sure you do. All right. You're familiar with that concept, right? Mm-hmm. Okay. All right. Good. Hold that thought. Now, you go deeper in the ocean, right? You go deeper in the ocean. Okay? All of a sudden, the water at the surface of the ocean, for example, is a lot warmer than the water towards the depth of how many thousand feet you're talking about, right? Mm. What happened to our principle? Our density principle?
Well, you're at a much higher pressure, for one, and there isn't as much penetration of the sunlight.
There's a much higher pressure, which would do what?
PV equals RT, so increase the temperature.
It should increase the temperature. It should increase the temperature. But why doesn't it?
Doesn't it? Actually, that's why the fish actually live in lakes. But I don't know how it does in oceans.
Not when you go really deep.
Steve, are you familiar with that?
I'm not familiar with.
It'd be cool if we had a board, but I can show you the gradients. But so as you get deeper, the ocean pretty much follows what's considered the geotemperature gradient. Are you guys familiar with that? There's also a lithographic gradient. Are you guys familiar with that?
No.
And just let me find out what's going on there. I did invite a lot of people. Maybe they're but so yeah. Let's see. Hey, Jimbo? Dude, I'm on Crawford. I'm in the middle of my presentation. It's, sorry, what's the address again?
1552 Crawford.
1552 Crawford. It's right catty corner to the Dome Church, coming up Pine. Okay? All right. So, anyway, that's an interesting concept, right? Do you know what the answer is?
No.
Okay, it has to do with the sea swells and the fact that the ocean currents always move the colder water beneath and the hotter water above, which leads to another question. But hold that thought. So here's a question for you. As you go down the temperature gradient of the Earth, right, you increase the temperature, you increase the density of the molecules, right? All of a sudden you have the weight of the Earth on top of you, right? Incidentally, and the temperature goes up. It unilaterally goes up. There's no exception to that rule in the Earth, right? Okay. But in the oceans, it essentially violates the principle. And so, if you're going to have this mixture of, for example, a miscible front, where, different compositions mix, right? You need something to describe it. and that would be what is classically known as the diffusivity equation, right? And I'm sure Sai has seen it and knows it backwards and forwards because it's very common in porous medium migration. All the hydrologists use it. All the petroleum engineers need it. The geothermal engineers are very conservative. So as the temperature gets thicker, right? As you pile this earth on, what is actually heavier? Were you familiar, for example, that what weighs more, a Volkswagen or a cubic yard of water? Would you say
The Volkswagen.
a Volkswagen weighs more?
Depends which Volkswagen you're talking about.
Is that true?
Yeah, because it's 1 cubic meter or kilometer.
One
Well,
cubic
it
yard.
depends on
It's close to
actually
a
the
meter.
molecular structure and how densely packed they are.
But
as well.
if we even assume that it's salt water and then we use the salt water density, even then it depends on which Volkswagen you're talking about.
Okay, so when you mix, how do you model mixing brine water with fresh water? Is that a concern, would you say, for hydrologists?
Yeah.
Obviously, right?
We use it in chemical engineering because they separate.
Yeah, stratified. It's
Exactly.
salt brine water is lighter
Exactly.
than actual water, right? The fresh water.
Absolutely. So actually, I do have this. A yard of cubic water does actually weigh more than a Volkswagen. It's weird, isn't it? That is weird. But what? So let's extrapolate that one and say. So now let's take a yard of earth. Which one weighs more? A yard of water or a yard of let's say barite or natural soil or
Earth.
refined. What's that?
Earth would weigh more.
What's that?
Earth would
The
weigh
Earth weighs way more.
Yeah.
Would you say way more?
Yeah.
Okay. What is the specific gravity of water?
One.
Sai would know that. Of course.
One.
Sharia would also know that. You're a chemical engineer, right? Yeah. What is the specific gravity of barite? Natural dirt.
I don't know.
Well, generally it's about 1.6. So, at 62 pounds per cubic foot, right? You multiply that by 1.6, and that's how much the Earth actually weighs. And that is what comprises the lithographic gradient. So you have the geothermal gradient, which it dictates according to a specific gravity of 1, and then you have the lithographic gradient, which is essentially mostly what the Earth, as you go deeper, follows. And so I can show you some of those things, but isn't it ironic that? So let's see, I had them and then I had to reboot. So that should be there. So the gradients. Okay, so here is the surface gradient. Normally, a good rule of thumb is that per 2,000 feet, you increase about 1,700 Celsius. That's about the temperature gradient. So when you consider that, what happens to the pressures?
What do you mean?
What's that?
What do you mean?
So does pressure, the internal pressure of the Earth, does it follow the temperature gradient? Is it inversely or unilaterally related to the temperature gradient?
Unilateral?
Exactly. They coincide. They're very close. This is all the way to the inner core of the Earth at 7,000 Kelvin. But everything the hydrologists deal with is way up here. and everything the energy side is dealing with is just a little bit deeper in respect, right? Too. But that's interesting. So you have different miscible fronts. There you go. So as you go even deeper than the ocean, right? Then you have your different gradients. See here, there you go. So lithographic, and then if you add alternative fracture, the pore pressures and hydrostatic. What it tells you is that you'll get bigger pressures as you go deeper than you will based on your hydrostatic head. Do you understand the concept of hydrostatic head?
No, not exactly.
Hydrostatic head is, do you know what it is, Sheree?
It's been a long time since I've had to.
I know sinus.
Like the vertical depth of water.
Yeah, the hydrostatic head is the weight of the water above you. The vertical weight. And you remember Bernoulli's equation? The sum of all the pressures has to be zero.
Sure.
So that's the hydrostatic, and this shows how that increases with depth, and lithographic, which is your specific gravity of 1.6 times bigger, is about follows pretty much a linear curve, and so interesting. All right, so moving on. Here's another example. But if I flash temperature or pressure up here, they both look very similar towards, okay. So those things are interesting. Now, all I wanted to do there was show that. And then, let's see, tabs. With respect to the diffusivity equation. Do you guys, so when we model a reservoir, a water reservoir, an aquifer, and if you're working for the state of Washington, you're very concerned about, fresh water and the runoff and the replenishment of water resources, right? If you're an energy engineer, right, you're concerned about usually much deeper than that, much higher temperatures and pressures, and you're also concerned with how to model, this environment, in situ condition environment. Well, so my thought is there are several ways that scientists have figured out to model that. One of them is finite elements, and the other one, as far as building math models, and another one is called finite differences. And I've tried to, I'm just playing around with Python and everything. I've tried to do the finite difference one. I'm getting more bold to try to take on elements. I actually did study it in school when I was in it many years ago. But you probably did too, right?
I'm not sure. The finite differences?
Yeah, did you do elements? Yeah.
Finite difference is nothing but the average of two at least.
Yeah.
Yeah, the finite difference is what's the main one? The center step. What's that?
Central difference?
Yeah, FCTS or something, right? Anyway, there's libraries for that already in Python. There's also libraries for the element method in Python already. And I've been playing around with them. I'll just show you where I'm at so far. Like I said, I'm trying to get better at this. But here are, so when you're concerned about modeling this process in the Earth, right, you get reduced to the diffusivity equation. Now, Sai, does that look familiar to you? That equation?
I mean, the partial differentials are, but I don't work with the same equations.
I mean, do you have
But
that?
they're similar.
You have that same porosity, viscosity, compressibility relationship?
No, I don't
You
work
get-
with them, but they're like with the similar.
Anyway.
Are you in the spherical coordinates?
What's that?
Are you in spherical coordinates?
Well, this would have been spherical coordinates.
Yeah, see that's right.
That's single
We
dimension.
work with rectangles. Yeah.
Yeah, well, it's similar.
Yeah, this is. Yeah.
So the diffusivity equation is really measuring whatever you're considering, I think it arose out of the study of heat. Okay, mechanical engineers would know about that. And if for example the gradient, the change in temperature with respect to the medium is linear, then you have like let's say right here, as the change in temperature, it creates like a front as it dissipates through whatever the medium is. Like let's say you put a hot iron on this side of the table and you want to see how long it takes for it to get over there, right? And it sort of goes in a linear path, right? So that would be the change in the distance with respect to the change in time. But it's usually how they model, because the change, it's the change in the change of distance, which invokes a Laplacian treatise on the distance as it changes with respect to time. So do you know about Laplacian forms, right?
Vaguely, yes.
Okay, so they are simply the second order evaluation of the change in change of whatever you're evaluating. Okay, so but now you want to do that with time. Now let's say it's nonlinear. Let's say you want to see how fast the temperature accelerates, or it's a mess. It does this, and then it becomes a second order partial differential with respect to both sides, with respect to time and distance. So the very simple equation is the change in time with respect to the change in one direction, the change in direction. So it's the change in time with respect to the second order treatise of the change in distance. That's the simple form of, and when you extrapolate that, Darcy sat there and watched it happen in a porous medium, and he built some parameters which were permeability. Now there are other parameters. There's connectivity. But mainly it was the pore space of the medium, the connectivity of the porosity of the medium, the permeability. What's that?
Hydraulic conductivity. If you look at
the hydraulic conductivity, the compressibility of the medium of the fluid that you're evaluating, and the viscosity, resistance to motion, to movement of what you're evaluating. So if you're treating a mixture of oil and water, that's different than if you're treating water and if you're treating just oil, just some kind of hydrocarbon derivative, right? So those were all the studies are related. And here, I think this is how it is, but this is diffusivity heat equation. It looks the same, only all the constants are different. So now, this would be a task, but I'm not going to do it for you. But you can actually derive, if you plug this equation into the second, and you come up with the first equation, which is the evaluation of the diffusivity equation. So let's see, minus, there it is in simple form, as you operate on x and t. Okay, which is, and this, I don't know, we're familiar with this. That's just a very, something that's very recognizable. I think the hydrologists use it as well. But now, Navier-Stokes, on the other hand. You're familiar with Navier-Stokes, right? Navier-Stokes said that, okay, instead of treating it as a potential, so when you talk about the diffusivity equation, you're talking about pressure, okay, a potentiometric difference, right? And when you treat the Navier-Stokes equation, includes an energy balance, a force and momentum balance, and a mass balance, all piecewise linearly incremented over a boundary. So you're solving all three of those equations at once and you use the characteristics of each of the equations to describe whatever the reservoir is or the aquifer. And because I know the hydrologists I know they have big conferences on using finite elements. I've even looked at their stuff. I cheated.
I'm going to talk about that.
Yeah, see, he's going to talk about it. So anyway, but that would be the Navier-Stokes. And here are some pictures of the Navier-Stokes series of equations. And I'm getting bold enough to try to do it myself in finite elements. But so you have a continuity. You have continuity. You have momentum, and you have kinematics, which is your energy. And these terms, like your T and your D, go away when you compile this thing into. But that pretty much follows the way you guys treat it, right? The hydrologists treat it, yeah. So here, here are the different terms in an energy balance for a in Navier-Stokes. Yeah. So it's all there. Anyway, so very briefly, although my code is not, I'll just show you what I've done so far, which is and if, okay, keep going. Where's that? Where'd it go? Okay. Okay, so this here, it doesn't work. I tried to map the difference between using an analytical solution and a numerical solution, and it's broken. It doesn't show it very well. And then I extrapolated that to, well, this is not the real. I wanted to extrapolate it, if I get 2 dimensions, into spherical coordinates. So I haven't actually done it yet. I just know I can get it to work if I finally.
Is this output from your code?
Yeah, this is my code. Yeah.
What do you use for plot?
I just use Matplotlib in Python. Matplotlib, yeah.
Yeah, but what's the command?
Oh, and then you got to build your little graph, with your axes.
No, for this one.
Oh, for this I use polar coordinates.
Right.
And
what's the Matplotlib command? Plot 3D or?
Yeah, plot 3D.
Okay.
But this isn't really real. I just messing with it because I want to be able to do it at some point. But I'll have X and Y against whatever I'm using. So if you want to see what I'm doing, and it's kind of broken, like I tell you. So anyway, that should have stopped. Control. Okay, wait a minute. Let's see. Did I know. Okay, but if I come back. If I'm in some kind of editor, yeah, it would, but escape and quit. So I will tell you what I'll do. I'll shut that down. I'll go over here. But what I wanted to show you is part of the numerical modeling thing, which is what I'm trying to do, which might be worthwhile. I don't know if you... Hey, Sharia, did you know where the bathroom is?
No, but actually I'm ordering.
Oh yeah, get some Pringles. There is actually a bathroom down there.
Okay.
Okay. So let me get back to my code here. So if I go to code and I get here, I had to move all this stuff when I got here. So I'm going, and then let's see. One of these I did have ready to show. I am actually. I'm actually my differential equation. I think it's right there. So show in. Here we go. Diffuse Python. D. How about that? And then I think show 202 dash sh. This should work. I think M, right? Yeah, M. So you probably use Python, right?
No, I use Anaconda.
Oh, you use Anaconda. My thing is, my engines are so wimpy. I just, I just want to keep as much memory free as I can. So okay, so here you have it. this, I'm evaluating U and UX on different places, and I'm incrementing through, and this is the resolution of the matrices, and yeah, I'm using a delta time, a delta X, a delta Y, and I'm evaluating the charge, and it doesn't show much changing there. I need to add some parameters, but just to show you that at every step it evaluates and then, you know, I get a thing on how long it takes me to process it and stuff. But that's the nuts and bolts of it. And so, anyway, at this point, trying to solve the diffusivity equation in Python, and I'm actually trying to do it myself as much as I can without, you know, using all the already prescribed Python tools, because everybody else has done it and they probably did it better than me, you know. But at some point, when I have my own tools working, I can. I have built some apps, you know, and I'll be able to claim it. But so anyway, here's so I built some little stupid things like this one is let's see, this is this is a statistics app. This guy, and what it does is it lets you evaluate you know, P and Z values for. And so for kids or students who use this, you know, they're trying to get through a statistics class, this is a great way to get to the answer real quick. And you know, and so I can run that for you, but it doesn't have much to do with diffusivity. And then I compute confidence levels and things for them and stuff like that. If you want a copy, it's you can easily download them. I'm happy to share it with you. Do you use statistics much? Yeah. See. Anyway, just one of the ones that I did do that I did dimensionless pressure. Now this one, again, you know, it's kind of the old logo thing. It's not exciting, but you can do engineering calculations. But here is dimensionless pressure, and what you have to do is you have to have meaningful values in stuff. I'm going to try to do it. And then you compete, let's say you had a 35 porosity capability, and then you had, so I need to compete a dimensionless time. I compete a dimensionless time. Then I try to get a dimensionless pressure.
You're doing a ratio?
Well, does anybody know what the advantage is of dimensionless pressure? Do you know? Yeah.
You don't have to deal with units, one, and then the other one is like you have a comparison to something that makes sense. Instead of comparing to stuff, you have a comparison to one thing, like specific gravity, for example.
Right.
So it's all related to water.
So is it like specific gravity in that it's a ratio?
Yeah.
Against a standard?
Yeah. And then you use it in the equations, you don't have to like be confused about it.
Okay, so then I compute a dimensionless time based on those reservoir parameters, and then I compute I get my pressure based on what the time you selected, and it tells me. So I had a drop, for example, in that case, whatever it was. If you're at 754 seconds out or something, you'll get a drop of 23 psi over. So that's based on these parameters of levels of production. It works the same for water wells, you know, kind of thing. That's true. So why is dimensionless? He explained it well, but what I was thinking is, so why is that advantageous? When would it be more advantageous to have dimensionless pressure if you're concerned about what?
An effect when you're looking at relative things, when you're comparing them.
Yeah, exactly. And at least the way I understand it, it has a lot to do with boundary conditions.
Oh, yeah.
So that, you know, the boundary conditions don't change your problem. Because you can assume, for example, right? I mean, I showed you the gradient, right? You can assume you have infinite pressure. But as you produce a water well, for example, right? you don't have infinite pressure. You don't have it. There are boundary influences, right? If you deal with hydrocarbons, the effect is much more pronounced. So, and if you're the guy that's making $1,000 a day, and your job is to flow that thing, because right now they're paying top dollar for, then you don't want to flow to the point that you essentially collapse the well, right? That you collapse the well bore where the oil interfaces with your capacity to lift it, right? So you have all these concerns. So you want to be able to model something that doesn't that isn't dependent on the boundary effects. Okay? So you can say, okay, to this point, I'll always have a replenished pressure. But as soon as I get to where I feel the boundary effects, I won't. I don't have them. See? And so that's a concern. So dimensionless pressure is used in these kind of computations. Anyway, I was just going to turn the time over to Zai. And,
how are you guys doing on time? Yeah. You guys are fine?
Yeah.
Okay. So I was first of all not sure how many people were going to come and what expertise they have. I will just talk about what I do in detail. You can stop me if you guys are. This is too much. Okay, so I need to I told you guys. I'm a PhD student at UW, University of Washington, and I'm working with two other groups, one in Colorado, University of Colorado, and then another one is Tulane University, putting together a Python toolkit for things to do something what Red is doing. So these computations and many of the simulations, like simulation worlds or modeling worlds. So on this slide, I'm showing you different applications of modeling, 2D modeling, for example. So I'm in hydrology, but geomorphology or hydrology, we're going to deal with these things. For example, catchment hydrology is trying to route water where it's going, and then there is soil erosion. That's the impact of water on soil and how that's contributing to the channel incision or channel creation. And then you have glacier dynamics, you have landscape evolution, like how are the mountains created, or how are faults moving related to each other. Then we also have like extraterrestrial, like it's impact cratering. It doesn't have to be extraterrestrial, it can be on Earth too, like if you look at impacts of a meteorite on a land surface. And then we also have like modeling volcanoes. These are only a few examples, and then all of these models have something in common, which is nothing but the base. Like every building has a foundation, and if you standardize that and you provide that as like bricks, then building is easier, correct? So I just said it's like all these models are like pizzas, but with the same base, with different sauces. So, and in the modeling world, if you ask Brett, he would probably agree that there is a time when you feel that this is too boring to pursue because you have been spending too much time on small details, and that's the sub-threshold, and you want to get over it so that you can let your passion drive. So we are trying to like bring people from here to here by providing the tools. That's the whole concept of why we are doing this. And the name of the toolkit, which is built in Python, is LandLab. And what we provide is a framework for people to build on. And for now, the support is only for 2D numerical models. But I don't see why you cannot extrapolate that to 3D. All the people who are involved until now are from Earth surface dynamics, but the grid system can be used for electrical systems also, or chemical systems, or groundwater systems, or anything if you need a grid or something like that. And what do we provide? One is a grid. So there are different types of grids that we provide. in modeling, we always like do calculations on different points. For example, you looked at the whole mesh, and what you want to do is like you want to make sure you can track all the elements, and if you want to like pinpoint the areas where something is happening, you need very good data structures to support that.
Sure.
So by providing a grid, we are providing a lot of data structures to make modeling easier. And then we also have components, or let people develop components. Each component is like an application. For example, if you're trying to calculate the incident radiation on a surface, which is sloped and has an aspect, then that can be implemented as a single component, which is standalone, so that people can like take it from this shelf and then match it with some other and make a couple components and make a model from it. So in LandLab, each component is a class, which is object-oriented language, if you guys are aware of it, which is nothing but a specialized function. Are you guys aware of programming as in specific? Okay. So, well, if you don't know about that, just we can leave that for now. But when you learn about those things, you'll understand. And then we also have some utilities for inputs and outputs. So if you know minimal programming, you will be able to do something useful, or just follow our examples and do something from that. And then we also have a cellular automata application, which is a standalone total model that has been developed based on the components that are available and the special components that were only coded for these. So cellular automata is nothing but repeating stochastically some rule sets and then coming up with a result instead of doing physically, like using physical equations. And now let's look at some examples of the models that were built. So this is an overland flow example. We assume that there is rainfall on this watershed, and then the elevation drops, and then we know that the water is going to travel from here to down this place. So this is plotting the amount of water that is being accumulated at the outlet. So this is the outlet, this is the higher elevation. So all the water on this watershed is actually coming down to this place. And this is giving you the time scale. This is the time scale of the storm, and this is when you will get most discharge in this place.
Is that real data, or,
oh, yeah.
or are you simulating?
No, this is a real data. This is a LiDAR data set, and then this is from a real storm data.
Nice.
Or maybe a parameterized data set, but in the sense storm data, but the landscape is a true one, and the value used is a legible storm. And now there is fracture. This is weathering and the effect of fracture. This is also again a cellular automata set, and this is a simulation of fracture. And now we are looking at landscape elevation scale types, where your valleys are forming at. So if you look, I don't know if you can look at the time scales here. But those should be. Oh, see, 46 kilo years. That's how. And this is my stuff. Here I'm simulating plant competition, and we're looking at the effect of disturbance like fire and grazing on the organization of vegetation. So here each green cell is grass, white is bare soil, and then the red color is shrub, and we're looking at a semi-arid southwest United States landscape. And on the right, we are trying to parameterize a soil layer and into a normalized, see, this is where normalizing is helpful. We're trying to normalize that to a -2 and to +2, and you're looking at the comparative and relative stuff.
So on a cyclical basis, the vegetation replaces itself.
Oh, I will talk about that.
Okay.
So we're saying that if there is a lot of resource, that means it's fertility, and then if there's less resource, it's not less fertile, and then that has an influence on the vegetation organization and the competition between the neighbors or neighboring cells. And we start with environment, for example, a natural fire environment where the fires are very frequent. And then we look at an environment of 1,000 years. We see that there's some kind of an equilibrium here. And you see grass dominating and shrubs are like way under-dominated, and then you subside the fires because this is simulating a Euro-American settlements here where they kind of control the fires, and then they brought in cattle. So that helped the shrubs to grow further. And the increase in percentage of shrubs is not a good thing, mainly because it's like they are invasive and then they take up all the resources, and then now we reintroduce, like we come back and we leave the place to be how it was, and then it kind of goes back to an equilibrium state, which was there before. So which is kind of interesting. So for these models, that grids are all like helpful, the components are helpful. And now
you're saying that the grazing has an adverse impact
on grass, because grazing here.
And the fires are helpful because they clear off the.
So fires are very helpful. So
as long as they don't burn the whole thing.
Yeah, exactly. I mean, controlled fires.
Okay.
So
which is what they used to do with the slash and burn farming and whatnot. Is there was a controlled fire.
Yes, exactly. The reason being, if you have an even ground, then shrubs are invasive when there's less moisture. And these are island dunes kind of stuff, like it's mostly arid and no water at all. So grass is already struggling to survive, and then the shrubs are like, this is my kind of place, and then they just drive
They
grass
take
away.
over the resources.
Yeah. So now what fire does is it kills the shrubs, and which allows the grass to come back, which is dynamic in the sense it can come back in short time scales.
Mm-hmm.
But shrubs take more time, so that's the competitive advantage that's providing grass.
Nice, yeah.
And then let's see how we can use land-lab grids. So here we're showing. Let's look at a model, a linear diffuser, which sounds familiar to you, right?
Yeah, sure.
So in linear diffuser, if we look at this place as a point on a grid, then we want to look at how much flux is coming in and how much flux is going out. And let's see how we can do that using land labs. So these are the grid types we have. And then this is the code to create a simple grid. So what this does is it creates a 4x5, 4 rows, 5 columns of grids with a 10 meter spacing. So now you have number like 20 nodes. I will come to the point of what nodes and links are in a second. And see, we have different data structures. So if we have 20 points on the grid, these are the nodes. That's the 20 points that you just created. And the area that is closest to a node is called a cell. So this shaded area is a cell. And that's the closest to this point. And then this cell is closest to this point. And there are no cells in the boundaries, just to because half of it is not a part of the domain.
And then you solve the continuity balance?
Yeah, mass balance and
those,
mass balance.
On those?
On the nodes or cells, depending
it's
on what you
Navier-Stokes,
want.
right?
Yeah.
Okay.
Navier-Stokes, I think it's more analytical, I guess.
Okay.
But here, this is all finite volume.
Finite volume.
Yeah. And what they do is they solve Navier-Stokes at each point, I think, each node, and then they kind of do the finite difference type stuff, correct? Finite elements type stuff.
Yeah, well, finite volume is like an extrapolation of elements. You consider things in terms of three-dimensional, or
Sure.
an extrapolation of whatever your piecewise linear grid was.
Mm-hmm. Yeah. So this is how we can represent stuff on these things. Should I go more in detail of like how to use it? Are you guys interested? I mean, I can like quickly talk about it.
Did you help build it?
Yeah, I'm a developer of this, but those grids and data structures are mostly dealt by the team in Colorado.
You use
University of
matrices.
Colorado. No, I use these.
Yeah, I know, but I'm saying.
Oh, you use matrices.
No, it's a huge matrices.
Oh yeah, yeah.
You know, it's a
Yeah.
1,000 by 1,000 matrices that you have to resolve somewhere. Can you run it on
Yeah, I run it on
the whole thing, or
Yeah.
just a window to it? Okay.
No, I can run it on fairly large grids.
Mm-hmm.
But ours is all like long one-dimensional grids.
Okay.
So once we get the data, so this is how we number them. So there are 20 nodes, right? So in Python, everything starts with a 0. So the naming convention is like 0, 1 to 3, and then so the cells are 0, 1, 2, 3, 4, 5. So 6 cells. Let's look at the perimeter boundary. The perimeters is dealt differently. So you can set boundary conditions and then extrapolate from there. Let's see, and then you can represent flow via links that are connecting the nodes.
Nice.
Let's look at an example. Here. So a field is nothing but if you have an array that is equivalent to the number of locations, then if you can, and that can be put on the grid. So when you have numerical modeling, a lot of time there are bottlenecks. There are different types of bottlenecks because time is of essence, and then the computing power is of essence. In Python, the way the data is organized is that once the data is like stored on the hard drive, then the address of it is being stored somewhere instead of the whole data itself. Like the data structures, there are different ways of storing them. One, you know where it starts and then tracking how many of them are there next. And then in Python, you just store the address because you can just send the address instead of sending the whole data and creating copies. To help that, we put fields which we can tag it along a grid, and then when we have to send a lot of data, we just send the address of the grid instead of the whole data again and again. So that improves the speed of the interface between different components. So that's a field, that's an example, and then you can create those. And we can read DEMs into the whole framework using S3, like the ArcGIS helpers. And then we also can do, let's look at an example. So this is a two-dimensional diffusion equation. Do you recognize that? There's no squares and then
Plus on.
So you're looking at flow, which is the change in elevation over time, and then which is nothing but sum of all the fluxes in and out of the domain.
Domain boundary.
And then T is nothing but a transport coefficient, so it can be written the other way. So if you solve that equation, you would get something like this. To do that on the grid, you look at a cell with a node here, and then you want to see how much is coming in on each face and how much is leaving. In the same way, you see for all directions. So that whole equation can be computed this way in finite differences and finite volume methods. So now that can be done using links. So I said these are nodes and then this is a link. So you can represent all this data on those using, so to do that you need to know how much is the gradient, like what's the difference between the values among the neighbors. You can do that simply using a function like this. So it's like using percentage on your percentage calculator on your calculator. So this is the tools advantage that we are trying to provide. And now that can be multiplied by t, and now you get dq dx. And you just can also, so there are two different things. Now you have elevation, but there might be water depth that you're interested in. So there are different ways of representing data. So here you are just looking at one data set, and now you know that this is higher value, this is a lower value, and you want to see the mean of the value, then it's 3.5 on the link. But if you're more concerned about the water depth here, you could actually you could change that easily by saying, okay, I want to do we want to map value, the max value or the mean value, but I want you to consider the other one instead, and then change it. So so this is one thing, and that can be like packaged into a small component. So it's called a linear diffuser, and you send in the input data, and then you can run, like you can execute that at one time step, and then you can put that in a for loop and do it over multiple time steps. And so these components are again like plug and play. You can just grab what you want. And this is my step. This is what I do for hydrology. So I work with eco-hydrology, and that's why I was so interested in ecology. Like, what do you do with the so as I told you, I work with plant competition. So that's another cellular automata model. I say these are the rules, and now I will generate random numbers, and then do this again and again, and see how the organization of vegetation changes. But there is a physical like input to it. It's not like a game, but it is supported by data and a very intense numerical physical model, which is nothing but this model here, the top part is a physical model which takes in the grid and looks at all the locations and takes in each storm over time, and then calculates the radiation that is incident, and it distributes the whole potential evapotranspiration, because potential evapotranspiration can be converted into how much vegetation can happen. The more the vegetation is growing, the more potential evapotranspiration there is. So that is being converted to like how much water or the moisture is there in the soil, and that's again converted to the leaf area index, which is nothing but a way to look at how much vegetation there is, or the biomass. And now, while doing this, at each time step, we can see how much stress the trees are or the plants are in. Because if there is less moisture in the soil, then the trees are actually struggling to grow. So that data, that value is being accumulated over 1 year and then passed on to this model as a cumulative water stress. And this model runs at each storm time step. So every storm, this model is executed and all the values are created and stored. And then now this model is running only at one step per year. So the way because the organization is not that dynamic, so we can cut down the time by doing that. And we run this model for like 10,000 years or 15,000 years sometimes, and we can see some like actual landscape type organization. I don't know why this is not so clear. So here we have like green is grass again, shrubs are red, trees are black, and then white is bare soil, and this is a little north of the previous location that I talked about. This is in New Mexico. It's also semi-arid, and now we start with the random distribution of random organization of the vegetation, but we also have like topography in there. So if you are facing north, if you are on the north facing slopes, then you will get less radiation than a flat surface or a south facing slope in this area. This is northern hemisphere, so that's true. And then we let that model run over 100 years, then you see some kind of clustering happening. I don't know if you can observe that, but actually you can see that. You see green are coming together, black is coming together. And you can see that pronounced here. I'm sorry you cannot see the underlying, what do we call that, contour lines, but the contour lines will show you that.
Oh, I see them.
Yeah, the contour lines are the elevation, the same elevation lines. And
So do you think the vegetation migrates?
Oh yeah. I mean, vegetation migrates in the sense
But it dies here and then it sort of flourishes over here
because it's sending seeds.
Okay.
So what a plant does is it grows and then it sends seeds around.
Spores, it spawns.
Yeah.
Yeah.
So that's how it migrates. It's not walking, but it's sending it's over time.
Can this be attributed to groundwaters?
It can be, but there's not much groundwater here.
Okay.
This is really semi-arid and there's very less water. So it's always like looking for water to use right away rather than having a groundwater system. Like the water table is like pretty deep in this situation. But yeah, groundwater does affect. So you can see that some clustering here. This is a real location that we used, and the trees like the north-facing slopes, and then the shrubs like the south-facing slopes. The reason being, trees cannot survive on the south-facing slopes as the moisture is depleted faster because of the high incidence of sunlight. This is in this region. So those are the type of studies we do, and it's open for public. This is an open source project, so it's available to you guys on GitHub. You guys can poke on it, and learning Python is very easy. So just try to play with it.
Exactly.
And if you have questions, we are on Slack. We are quite active. If you face problems, we can talk to you guys immediately. You can also create an issue on GitHub, and someone will talk to you about it.
Great.
Thanks for listening.
Yeah,
Yeah, thanks.
Thanks a lot.
Do you want to see something happening?
Sure. Yeah. Did you want to say a little bit? Let me write that.
Oh
down.
yeah, you should.
Or you just have it on a business card, right, or something?
Me? Yeah.
Or just give me your business card or something. Because I'll pull it down and play with it a little bit.
Sure. Yeah. Write it?
Yeah, sure. Thanks. Yeah. Sheree was going to tell us a little bit about her pop's business, right? A little bit, or?
Yeah.
Okay.
So I think especially since most people here are not in oil and gas, so I'll kind of just talk in general about the process. So Brett was talking about using these numerical models and these models to kind of find the reservoirs and find how much is in the reservoir, what it looks like, where it is, that sort of a thing.
Did you want this on? Did you want?
Oh, I don't care. Yeah. Oh, well, whatever.
There you go. Go, girl.
And so the way that they create these reservoir models is that they shoot seismic data, essentially, so long-range seismic data. And the resolution is about 20 feet. And it's all shot in time. And so then they also use this thing called acoustic logging data, which is where they will drill an exploratory well, let's say, and then they collect shorter range, so the depth penetration into the rock is about 6 inches, and they collect this acoustic logging data, and it ties time to depth. That's the essential purpose of it. It's tying time to depth, and then they use that to build and create depth and frame of reference for their seismic models as well. And they use that in geomechanical models. So the acoustic log data is also used to find your Young's modulus or
Poisson's ratio.
Yeah, Poisson's ratio, all of this stuff, and they use that throughout the models in a variety of ways. And so it can be very damaging if the acoustic logging data has a high margin of error in it, which error can creep into it from a variety of sources. I mean, one, there's just error inherent in any sort of measurement, some error, but error can be added to it because if the data is being collected while there are drilling operations going on, for instance, the drilling noise can affect the acoustic waves and can change the time. And so it's essentially changing what the formation looks like, right? So like if the waves have traveled through the formation, it's apparently faster, then it's a harder formation is what it's telling the model. And so that can change where they place future wells. It can change how large or small they think the reservoir is and how economically viable it is. It can change a large number of things in there. It can change the drilling factors, completion factors for the completions engineer, right? Because they want to perforate a certain amount or use certain drill bits or things like that. And so if these data points are incorrect, it could potentially affect all of these other factors, right?
So you run this after completion? I mean, you already have a well in existence.
No.
It's before.
It's after the well is drilled, before it's completed.
Yeah.
Yeah,
Okay.
and before it's cased. Mm-hmm. So a lot of times, like he was talking about collapsing the reservoir, not just to protect the water table, but also to prevent collapsing the geological formations under there. They will case the well a lot of times. They have to case it in the vertical. They don't always case it in the horizontal. So casing means that they cement it, essentially. So they form a cement bond in between the wellbore and the formation, and run these tools also to try and determine how well it is cemented.
So initially they're going to have seismic data, right? That's what gave them the idea in the beginning, right? So
right.
What you do is you go deep, you go into the well, and you have tools, right? You Papa has trucks or something?
No. Service companies have tools. These are widely used.
Mm-hmm.
There's,
And then you run.
We process the data that is collected. So
and you wait for it to come back. In other words, you wait for your audio to come back, or
it's not. It's very fast. It's only going like the tool. It's going 6 inches. Mm-hmm. So the acoustic data is traveling a total of 2 feet. So the difference is, your reservoir model and your seismic data is integrated over a large area, but the acoustic logging data is measuring the acoustics in a discrete point.
Right.
But the tool is moving like this down the wellbore. So each depth point, so it's measuring every 6 inches, and it's discrete 360 degrees at each depth point, but each depth point is hit about 300 to 500 times, depending on the tool, at each depth point. So that is the size of our matrix that we're working with at each depth. And so over 5,000 feet, every 6 inches, you get like about 300 to 500 data points, right? And it's collected, the data that we specifically use, some of the data is just omnidirectional. It's just this pulse that goes out. But our data is oriented. So it is collected in 4 sectors. So 360 degrees around, we can figure out essentially which sector it's coming from. We have like assumptions. And there's like a true north that we assume on the tool. And so everything is oriented towards that point from the tool's perspective. And so essentially what we're doing at each of these data depth points, in general, this is what petrophysicists or acoustic log people do, is at each of these depth points, we're doing a root mean square analysis, and we're finding like an energy or a value for each of the 90 degrees within that sector.
You're essentially better approximating the pay zone.
Yeah.
Where to perforate, where to complete.
Right. So that's what we have been moving towards. There are a number of different tools which can kind of help with approximating it. There are a number of theories floating around, like do fractures matter, do they not matter, all sorts of things. But we do know that stresses within the formation matter, and that's the one thing that acoustics is very good at reading is the stresses within the formation. And there is compressional stress and there is shear stress. So compressional stress is going in the same direction as the particles, The shear stress is going like this in an X and Y direction, and you'll find both stresses within the formation. And so acoustics can map both the shear and the compressional stress, which is what we're doing. And shear anisotropy is what the shear stress computation is called. And what we're doing is that we got our patent on was that we're using the compressional waveforms sectored, so oriented, and we are mapping the energy drop across the wellbore. So essentially what's going on is that we are normalizing the waveforms because each of the receivers are going to have slightly different outputs, and so we want to normalize the waveforms from the receivers. We're stacking the data, which means that because it's all being recorded in time, there's going to be a lag time between certain receivers, and so we're trying to remove those lag times and stack them all together so that we're assuming that they it's all occurring starting at the same time, so that lag time doesn't factor into it. And it's also combining waveforms, right, to stabilize them, because we're essentially looking for anomalies. We're not, and so the noise should cancel out. The anomalies that really are worth something should stand out more when we are averaging waveforms, right? So we're looking for these anomalies. So we get our 360-degree view of it, 90 points. We find the minimum, the average, the maximum value, and along with those, with the minimum and maximum, for instance, there's an associated theta. So we're looking, because it's looking at this slice, 90 degrees here, so there's going to be 0 through 90. It's going to have the minimum occurs at, 0.25 in the matrix, so that's 25 degrees. So that's what we're essentially assuming. And so we are finding it's essentially like a differential between the minimum and the average. So because if the waves are traveling through a homogeneous geological formation, they're essentially going to be the same. There's not going to be much difference between the minimum and the average if the formation is homogeneous. But if it's highly stressed, so highly compacted, if that stress has culminated into a natural fracture, then as it's traversing that highly stressed, highly compacted, there's going to be a drop in energy, or apparent drop in energy. That's how it's going to look. So we are mapping those apparent drops in energy, trying to figure out in what direction they are going, and those will be planes of weakness, essentially.
Yeah, what do you do then?
We give that data, so we're creating a curve. We just create a curve that goes along the depth of the wellbore. We hand that over, and they can use that in their completions modeling, in their reservoir model, to figure out, so right now, maybe people who aren't that familiar with oil and gas, they don't know how to map these things that well, predictably. Especially not without spending a ton of money on core data, core samples, and then, or on imaging tools or things like that. So they essentially place their fracs or their perforations, sometimes it's acidizing, at just intervals. They're like every 100 feet we're going to perforate because we've explored this basin quite a bit and that has done well for us in the past. So they're not necessarily targeting certain areas. But if we can tell them that these are planes of weakness, they're more likely to open up and create flow paths, then they could potentially save money by not perforating areas that are unlikely to produce a flow path.
It would collapse the thing.
Yeah.
But how would you know a flow path if you are only going 2 feet in? Don't you need a longer connection for the flow to happen?
Of course you need, yes, but
you at least get the direction.
you get the direction that the stress is going in.
Oh, right.
Where it's intersecting the wellbore. So you know that if you perforate or somehow try and target this one area, that it will propagate in this general direction, which is where oil is potentially going to come from. The opposite side of the coin is there might be some formations where you don't want, you know that the stresses going in X direction go to the water table, and so your well will start producing water because that's what's happened in the past, whereas the stresses that go in Y direction will produce your oil or gas. So you want to make sure and avoid the ones that go in the perforating in any area that goes in the X direction, because one, it ruins your well bore. You have to plug it. You can't do anything about it at that point. And two, it could be potentially really damaging to the environment. So that's essentially, and then, so what I had started talking about was like the noise. So all these different factors create noise. The tool creates noise, ideally you assume that the tool is like right in the middle of the well and it's going down perfectly, but it's going to like knock against the walls of the well bore. It might just be tilted off to the side the entire time. You don't really know. So it creates a lot of noise in the acoustic data. Typically, or the current standard is that they do a frequency domain filtering, or they do a frequency and time domain filtering. So this is where your Fouriers and Laplaces come into play, switching between frequency to time domain. But we've found that the noise oftentimes overlaps both in frequency and in time with your formation signal. And so frequency and time domain filtering don't eliminate that noise, at least not effectively, and can often create these errors where they skew the data in one direction or the other, either being too fast or too slow. So we're using something called predictive deconvolution, which is just a fancy way to say we're inverting, subtracting out matrices from each other. So we're defining a noise spectrum and then subtracting it out from the total spectrum of data, these matrices, and isolating what we hope to be is the formation signal and eliminating the noise signal.
Who did all your math for you?
My dad wrote everything. Well, I did some of it, but conceptually, but not actually.
Are you pretty good with Fourier series?
Not as good as he is, because when he started, he was doing them all by hand. So when I was in school, we had computers to do them for us.
So you contract with the service companies?
With operating companies.
Operating like Halliburton or Weatherford?
No, so Weatherford, Halliburton, Schlumberger are our competitors.
So you have
our own software.
Yeah,
so
you have your own software, but you have your favorite service companies that go out there and run wireline tools for you.
But the oil companies own the data because they're paying for it.
Yeah, sure. And the oil company is the company man, right?
Yeah.
And
so
he's
they
always
give us
there.
the data. We process the data and give it to them.
Okay. So you contract with some service company to give you the data.
Well, yeah, we deal directly with like the Chevrons or Shells or whatever company, oil company, their chief petrophysicist or geophysicist gives us the data that they collected from Schlumberger or whatever.
Okay, gotcha.
Yeah. So,
how's it going now, though?
So we're seeing a lot more interest in a way because
the price of oil is slowly creeping up again. But
not just because of that, but because people are upset about, they have more time to look at their data, and then they're also upset about the way the service companies kind of they process things in a black box almost, like they don't explain to them.
We're good, Bill. Thank you.
Yeah.
Thank you. Thanks for letting us.
We're seeing some more interest from people because they want to find a way to kind of lower costs for themselves.
Exactly.
Yeah.
Sounds good. Well, thanks for sharing that.
I'm wondering how they could get like less diffuse data that makes sense. So I was in a lab where we used ultrasound different ways, but mostly to characterize defects in rail lines, so like in metal. I was not directly involved in it. I was working with ultrasound on a different thing, but once they tried it on concrete, it gave something that made absolutely no sense. So characterizing anything was such a mess. So how is that someone is dealing with anisotropy and
Yeah, they haven't put the concrete in yet.
no, not
So
concrete, but
bouncing off
like
the
the Earth's surface is so anisotropic. Concrete is difficult.
So that's
because
part
it's
of the reason why
anisotropic.
we're using the compressional waveforms,
Right.
because if there is, I think, more than 20% anisotropy within the formation, which not all formations are, the tools are not sensitive enough to discern the difference
Yeah.
between the anisotropy in the formation and like other aspects of the formation. So, but I would imagine that probably some of the difference comes in with how sensitive the tools are, the frequency at which they're sending out these acoustic pulses, and the fact that